So our next speaker is going to hopefully generate a lot of excitement from all of you as well. So this is Professor Konstantin Batygin, who also comes from Caltech. So I'm particularly honored to present him here. He's as he'd like to put it, he's Henry Kissinger's older brother because his hair is usually all sorts of different colors, including gray. But really, he's very young, but his hair does take a different color each day that I seem to see him. He also would like to make a disclaimer that he's not responsible for killing Pluto. It was actually his senior colleague, Professor Mike Brown, and he was only an undergraduate during that time, but he certainly had a big role in that. Maybe he'll even share some of that with you. I also learned that besides being brilliant, he really likes numbers. So for example, it's Planet 9, and he's the lead singer in the band called the Seventh Season, so he likes odd numbers. So I hope that after this talk, you will all recognize with me that he's certainly number one in what he does. So with that, please take it away, Konstantin.
Thanks, Julia. All right, well, thanks, everyone. Yeah, so astronomy is kind of a remarkable science in that it's kind of the oldest form of kind of natural philosophy. We've been doing astronomy as a humankind, I think, longer than we've been doing physics. And you know, the modern form of astronomy, where you kind of look up at the night sky using a telescope and see what you find, really began with Galileo's adoption of the telescope as a scientific tool. What's remarkable about this past 400-year period during which we were no longer limited by the resolution power of our eyesight, is that, you know, in terms of finding planets in the solar system, it has been an exceedingly unproductive venture, right? Using the telescope, we have found exactly one planet in the solar system that wasn't known to the ancient civilizations. So remember, everything out to Saturn, right? Mercury, Venus, Earth, of course, you know, Mars, Jupiter, Saturn, you can just see with your naked eye. So the ancient Greeks, ancient Romans knew about it. So the first planet that was not known to the ancient civilizations was discovered in the late 1770s, I believe 1776, by a royal astronomer named Herschel. And he was a very meticulous character. He would draw what he saw every night. And then he noticed that one dim star was slowly making its way across the night sky and recognized that indeed this is a planet, made a big deal out of it because the UK had Great Britain had lost the war, and the king was kind of depressed. He named it George, right? So we have Jupiter, Saturn, and George. And weirdly, the international astronomical community of the time was not super happy about this name. So they said, we'll have to change it to Uranus instead. So they did. And what's remarkable is that immediately upon the discovery of this new planetary member of the solar system, it was recognized that this planet was not following the trajectory that it was supposed to. See, even though Uranus was discovered by Herschel, it had been observed numerous times by other astronomers that preceded Herschel, right? So its orbit was immediately reconstructed by going to old notebooks and legacy observations of other astronomers. And really the kind of complete picture was put together by Alexis Bouvard in 1821, where he published a sequence of tables where he demonstrated that indeed Uranus was not where it's supposed to be. And you can tell from the slide that that's what's going on, because there's cosines and sines on the right-hand side, and there's a table, right? There's a big problem in celestial mechanics, right? Uranus was not following its predicted trajectory. So being a good theorist, Bouvard in this text proposes two solutions. Solution number one is you shouldn't trust the data, right? After all, it's just like astronomers drawing stuff, right? It's just not reliable. But he also mentions that on the off chance that this is right, okay, then you cannot exclude the possibility that what's happening is that beyond Uranus there exists another planet that we do not see that is pulling on Uranus and causing it to deviate from its predicted trajectory. So that deviation is actually holding information about the next planet over. Remember, this was 1821. It took a couple decades for the promise of this data set to really come to fruition, and the character that is typically credited with the mathematical discovery of Neptune is this guy, Urbain Le Verrier. So Le Verrier did this exceedingly complicated, beautiful set of calculations where he pointed out, he basically was able to, from the orbit of Uranus, from the deviations of Uranian motion, was able to demonstrate that indeed you can explain this away if you introduce a new planet into the solar system. And his manuscript looked like this, right? Clearly a total mess, but he got the right answer. In fact, not only did he get the right answer, he predicted the location of Neptune on the sky with an error bar, which was 1 degree. Okay, and he said, you just point over there. The French astronomers of the time were like, this is pretty cool math, but like, you know, you're kind of asking us to make a big commitment because like you have to stay up all night and be at the telescope, it gets cold. Like, we're not doing this. So in the end, it was actually a German astronomer named Gall who discovered Neptune in 1 hour. Right, he had all this entire observational campaign planned out, went up to the telescope, opened the dome, found Neptune. The end. So this was 1846, and since 1846, we have discovered 0 legitimate planets. There was kind of a close call with Pluto, but long story short, Pluto is like 5,000 times smaller than the Earth. It really is not a big deal. But what astronomers have uncovered over the past 2 decades is a field of icy debris that lives beyond Neptune. Okay? And so here's the solar system to scale. Okay, we have Jupiter. The pink circles are Jupiter, Saturn, Uranus, and Neptune. Very, very close in is the Earth. My house is actually right there. And in blue is the orbit of Pluto, the original member of the so-called Kuiper belt, this belt of kind of icy asteroids. And these are all of the objects that we know the orbits of very well today. So if you kind of just look at it in physical space, the Kuiper belt looks kind of like a ring of material that lives at about 40 times the radius, the orbital radius, compared to that of the Earth. Okay? So the dynamical structure of the Kuiper belt is actually really interesting, and it has led to a very tangible and real revolution in our understanding of how the solar system formed. I could give an approximately 8-hour talk about that, and maybe we'll save that for next year. For the purposes of what I'm going to talk about right now, the only thing you need to note is that all of these orbits, all of these orange circles, basically come to hug the biggest pink circle. Right? They're physically attached to the orbit of Neptune. Why? Because the Kuiper belt, this field of icy debris, was placed where it is today by Neptune. And gravity is a conservative force, meaning that if you kick something onto some highly elliptical orbit, it's going to come back to the place from which it started. So all of these orbits, even though they will evolve chaotically over many millions of years, they still remain gravitationally tethered to Neptune. That's a rule of thumb for all of these Kuiper belt objects. So the first exception to this rule was discovered by my partner in crime on this work, Mike Brown, back in 2003. Pluto's demotion was 2006. In 2003, I wasn't even an undergrad. I was in high school. But I was, as I like to say, I was still clearly giving Mike high-level kind of directions to find these things. That's actually absolutely not true. Not only was I was basically unaware of any of this. Now look, Sedna, right? You don't have to be like a sophisticated astronomer to realize that something's wrong, something's different about the orbit of Sedna compared to the rest of the Kuiper belt, right? First of all, if you look at kind of its furthest point from the sun, it goes out to 1,000 times the distance between the Earth and the sun, so it's exceedingly long period. It takes it about 11,000 years to go around the sun once. But really, that's not the most dramatic aspect of this orbit. The most dramatic thing is that actually at perihelion, when it comes closest to the sun, it doesn't come anywhere near Neptune. Right? So this means that Neptune alone cannot explain this orbit. Neptune did not play the only and dominant role in placing this object where it is today. And you can basically check this by running n-body simulations on your computer. If you just evolve this orbit for 4 billion years, nothing will happen to it. It'll just stay there. Slowly, slowly, it will process. But nothing really dramatic will happen. So for a long time, this was the only exception to the rule. And when you have one kind of data point that doesn't fit with your story, the standard explanations that scientists go to is like, well, you know, something bad happened to Sedna when it formed, like, got kicked by stuff and messed up by stars. I don't know, it's bad. Just it had a bad history, okay? But in 2013, okay, a second object having this this property was discovered, and then it's just like, okay, we have 2 data points. It's time to look into this more closely. So the first thing that Mike and I realized, this maybe back in 2014, is that if you just look at all of the most distant orbits in the solar system, they all swing out into the same direction. So these are the most long period orbits that we know of, right? You can sort of tell that they're all pointing that way, right? If you rotate this around, they're all inclined by similar into a similar direction. You can almost put a piece of paper through that collection of orbits, and that's weird. You can ask yourself, what are the chances that we would see this clustering by chance? Right? That's the answer is 0.01%. Okay, and I'm not really a gambling man. And importantly, if you were to leave this pattern of orbits alone, they would eventually disperse. And by eventually, I only mean like 50 million years, right? Geologically short timescale. So something else is currently confining these orbits, holding them together. Now, the good news is, okay, the celestial mechanics, the study of how things move on the sky, has been around for about 400 years. Okay, so there's been a lot of mathematical machinery developed to tackle these types of problems. So to leading order, you can more or less do some estimates just on the board. Now I'd like to spend the next 45 minutes explaining this. Okay? So what you come up with is a Hamiltonian. No, okay. In reality, all that you can successfully get out of the calculations that you can do on the board are characteristic numbers, right? If indeed a planet exists in the solar system that is keeping these orbits together, then what mass does it have within a factor of 2 or 3? And what kind of orbit should it have? Should it have a circular orbit or an elliptic orbit? So from just doing calculations on the board, you can demonstrate that if a planet is responsible, it has to be big, right? It has to be a few times more massive than the Earth, at least. And secondly, its orbit has to be appreciably elliptic, unlike all the other orbits of the solar system's giant planets. Now, despite evidence in the news that points otherwise, we no longer live in 1846, okay? And we have computers now, so we're not limited to just doing calculations on the board. And indeed, one of the greatest things about being a prof at Caltech is at Caltech we have sort of incredible computational resources that are available to us. So the kind of program that we undertook was to really solve this problem by by large-scale computation. So we did thousands and thousands of numerical experiments, much like the one we see here on the board, where you start the solar system in its primordial state, when the Kuiper belt just formed, and it looked like an unstructured set of eccentric orbits, right? Just a randomized, kind of freshly generated belt. And then you introduce the solar system that we know is there, plus Planet 9, and you vary the parameters of Planet 9 in each simulations to see what fits best, then you allow it to evolve for the lifetime of the solar system for 4.5 billion years. So you, at the end, generate a synthetic Kuiper belt, and then you compare that synthetic Kuiper belt to the observed reality that you see through a telescope. And you ask, do you ever get as good of an answer as what we see in the observations? And it takes a long time, but right about now, at this point through the simulation, we're about 2.4 billion years into the lifetime of the solar system. You can start to see a pattern emerge, right? And I think, let me know if I'm the only person that can see this, okay? Because then the whole thing is just wrong. But I think at this point you can see that all of the surviving orbits are starting to point opposite of the orbit of Planet 9, right? We're all on board with this. So what's happening here is actually Planet 9 is locking these objects into resonances, into orbital resonances where the gravitational interactions between Planet 9 and the objects becomes coherent. And that's how it maintains the stability of this anti-aligned group of objects, and everything else gets ejected from the solar system into just space between stars. Okay? So by performing thousands of these calculations, we basically gain an understanding of what a synthetic Kuiper belt would look like as a function of Planet 9 parameters. And we can then go back to our data and fit, right, ask the question of which orbit fits best. And it turns out the orbit looks sort of like this. It's appreciably elliptic, not quite as elliptic as a comet, right? But very different from that of a typical planet like Jupiter, Saturn, Uranus, Neptune. And it's also appreciably tilted with respect to the plane of the solar system by about 20 degrees. So that's kind of what we came up with, and we were relatively proud of ourselves and gave ourselves a B+ for this work and decided to publish. Okay? But while we were preparing our first paper, notice something interesting, right? So every time our calculations would form a successful Kuiper belt, right? So we would also generate another population of objects in the distant solar system that are not observed. And that is summarized on this plot. I have a graduate student who has advised me to never show this plot, okay, because he says it looks terrible. And I sort of agree, but there's only really one way to demonstrate what I'm trying to say. So here on the y-axis is the inclination, the tilt of the orbits, and on the x-axis are the orientations of the orbits. So the population that I just talked about clusters around 180 degrees, but in all of these simulations we also get this population of bodies whose orbits get tilted and flipped upside down. Okay? And we thought this was really, really strange until we realized that we were filtering our data. We weren't plotting, okay? We just weren't looking at all of the entire data set. And when we went through the entire inventory of detected objects, what we found is that not only do such objects exist, okay, they basically fall exactly where our model predicts them to be. So as it turns out, the solar system also hosts this vast population of orbits that are exceedingly long period. It takes them 20,000 years to go around the sun once, but they're also perpendicular to the plane. And the only way that you can successfully generate orbits like this is through the gravitational influence of Planet 9. So I think that, for me at least, is the kind of most convincing line of evidence, even though it wasn't really part of the original story. Right? I think this is quite quite remarkable. There's one more thing that happened, which is kind of a fun story that I'll tell. I was on a run like a year after all this, and a friend of mine called me, who's a reporter, said they found a Kuiper Belt object that is orbiting the solar system in the wrong plane. It's not doing the right thing. Its plane is almost 90 degrees tilted, right? It's almost orbiting the solar system in this perpendicular sense. Can you comment? Right, and I said, well, yes, I can, right, and I told her this exact story. I said, blah blah blah, Planet 9, it generates these long period orbits that are tilted. And when I got back to my office, looked at the picture of what has been discovered, it was totally wrong. Right, it was an object like this, which was almost on a circular orbit, parked right next to Neptune. It was kind of embarrassing because I made all this big deal about Planet 9. But then I decided to check something, because during those simulations, right, you may have noticed this, but a lot of those blue ellipses disappeared, right? They disappeared because they got either scattered out to infinity, or they got scattered inwards into the inner solar system. So I decided to check the fate of all of these objects that we in the end delete from the solar system. And turns out, here's a representative evolution. By representative, I mean I chose the best object to kind of characterize what I'm going to say. So again, here we have Planet 9. There is the orbits of Uranus and Neptune. And in yellow is the orbit of the object, some random Kuiper Belt object. And it's doing some chaotic dance, but importantly, every time it hugs the orbit of Neptune, it gets scattered inwards. So its orbit shrinks, okay? And in time, what happens to this particular object is it gets locked into this perpendicular state. And I guess all I'm saying is that at the end of the day, if you liked it, then you should have put a ring on it, and that's clearly the evidence you see on the presentation. So these types of perpendicular objects are also kind of in an a posteriori sense explained by Planet 9. So this was motivation to go back and look through, again, the data set. Turns out that the number of highly inclined bodies in the Kuiper Belt is actually huge, right? And by huge, I mean of order 8 or something like that. And this one body was not actually a big deal. In retrospect, I'm not sure why it had made the news, because there had been many such detections. And if you check where Planet 9 places the objects, it successfully explains all of these data points that cannot be attributed to just formation of the solar system. So I think at this point, I'll skip this and merely mention that what we have at the moment is gravitational evidence for the existence of Planet 9, right? We have all of this distant structure of the solar system that we can only explain if Planet 9's gravity is there, but we haven't seen it using the telescope, and the search is on. Okay, so Mike and I have our own program. We actually have a great collaboration with colleagues from Japan. We're using the Japanese National Observatory to look for Planet 9. There are a couple other groups, including one that's led by my former student at University of Michigan, and she's pretty good. So they might find it first. But we will, my hope is that on the time scale of about 5 years, maybe a decade, right, our solar system will be back to having 9 planets. And because you guys have been so kind to me, I'll just tell you where it is on the sky. Okay, so this is the sky. This one right here is a constellation named Orion. And if our models are correct, we should find Planet 9 somewhere in this region. Okay, people tell me that's not Planet 9, and I tend to believe them, that star right here. But I think the most likely place for it to be is right around over here. Okay, at this point, I'll stop talking, and maybe Julia and I can chat a bit.
Wow, this was a fascinating talk. Thank you so much. I'm sure everyone was able to absorb everything.
There will be a quiz.
Yeah. So we would be happy to take some questions from the audience. I mean, do you want to take a seat? But I want to start off by suggesting this. So you very nonchalantly introduce length scales and time scales of, just a mere 40 billion years or 15 million years, 20,000 years. Everything is in many thousands of years. And how can you run simulations that can represent 4 billion years or something like that?
It's one heartbeat at a time. That's actually a great question. And for the longest time, you couldn't. So there's been a huge renaissance in this field of studying motion of planets and motion of like small asteroids, stuff that are affected by the planets over the last 2 decades, because suddenly computers got fast, right? So we've only been able to do this work because of the confluence of 2 things. Number one is that computational technology is now there to do these types of problems, and it's only been there for maybe a decade. And finally, there was kind of a coincidental unveiling of this distant solar system. The realization that Pluto is just one ice ball that's part of this whole belt of other ice balls, and studying their structure allows you to do this problem. So yes, it's computationally intensive, and the last set of simulations that I did related to this problem actually just finished last week, and I started them on Christmas Day, right? So it takes a while.
Of which year?
Of this year. 1998.
So how long does it take to compute an orbit for a particular planet?
So
you start on Christmas. Is it always run into the summer?
Not always. It depends on it depends on how many small bodies you want to simulate. So if you just want to evolve just the planets, you can do it in a matter of maybe a week. Okay? But all the time goes into resolving the evolution of the small bodies, and you need to integrate just a ton of them, because most of them just leave the solar system. The solar system has ejected 20 Earth masses of material over its lifetime. So most of this stuff leaves, and you're just chasing the 0.01% of the remaining particles and trying to construct statistics out of that. So they're computationally extensive and expensive calculations.
You can see that. That kind of makes you appreciate that everything is made out of atoms, but then there are computers that are also made out of atoms that can simulate the motion and the lifetime of something that takes 4 billion years to do something useful. Can I just ask one more question before we move on to the Q&A from the audience? What exactly is an object that we're defining in terms of the celestial pursuit? So to us, an object is something that has rigidity, right? Something we can touch, or something tangible, something tangible. Mm-hmm. So, but a planet can be cold, can be hot, the sun is made out of all sorts of plasma and very hot stuff. How do you is Planet 9 cold? Is it hot? Does it have solid in it? What is it?
It's even colder than Siberia. So it's as cold.
Okay.
Yeah. So
is it colder than Titan?
Actually, yes. So it's a great question, because I mean, in the end, what you're asking is there some interior heat source, right, that's keeping it warm? In the case of the sun, it is the conversion of hydrogen to helium, right, which maintains the 6,000 degree temperature of the surface. In case if you turn down the mass of the sun by about a factor of 100, what you would get is something that's called a brown dwarf, which is not quite a star. It's not quite a planet either. It's something that has high enough pressures at the center to burn deuterium for a while. So it kind of burns, but eventually it runs out of fuel and acts like a planet. And then finally, below 13 Jupiter masses, you have the planetary regime, where you have objects like Jupiter and eventually the Earth, where the only heat that you get from it is from radioactive decay and continued gravitational contraction. So Planet 9 is indeed a cold object. If you go and touch its surface, which we don't know what that looks like, but if you define some photospheric surface, it's probably going to be 40 degrees Kelvin. Right, so
it's pretty close to absolute zero, actually.
Yeah, pretty chilly.
All right. So any takers for moving to Planet 9 yet? All right, I think this is a good time to start taking some questions. So I see some people lined up here.
So, excuse me, first, that was really fun. Moving on to the frivolous, though. First, how do you define a planet as opposed to a planetoid or some other smaller object? Who gets to name the planet, and how is the name chosen?
Okay, all of these are excellent questions. So the current definition for what a planet is, it was actually constructed in 2006 specifically to define what a planet is not. Okay, in order to demote Pluto.
To demote Pluto.
Yeah, so currently the definition is you have to have enough gravity to become a sphere. That's actually easy to satisfy. Second definition is you have to orbit the sun. That's also easy to satisfy. The third one is the crucial one, which is that you have to clear your neighborhood of small debris, right? So you have to be the gravitationally dominant object. And one way to think about that is when we looked at the structure of the Kuiper Belt. The Kuiper Belt has its structure exclusively because Neptune is there, right? Neptune completely dictates what happens to these objects. They don't back react onto Neptune. So that makes Neptune a planet. Pluto is inconsequential to the evolution of these objects. So that's why it's a planetoid. But really the difference, as I see it, is close to, what is a continent versus what is an island, right? I mean, Australia is clearly a continent, but you have to put some arbitrary radius to your continent to make it not an island. And the second question of who gets to name it, there isn't a great and consistent history of planet naming in the solar system. Of course, as I mentioned, Herschel wanted to name Uranus George, and Leverrier wanted to name Neptune Leverrier. So kind of there isn't a consistent set of rules, but there is an online petition on change.org addressed to yours truly to name the new planet David Bowie. And I kind of like it.
That would be the ultimate gesture.
Well, that's a great act, a hard act to follow.
We should try it out. David Bowie, Planet David Bowie.
So Planet Bowie, it
Planet
can have
Bowie.
like
Neptune, Planet Bowie.
Ziggy Stardust as one of the moons. It's going to be great.
Go ahead,
My
Ken.
question is related to your comment about now the search is on and you're using the telescopes in Japan and other places. Is there any potential to take advantage of space missions that have the ability to have improved seeing conditions to accelerate the search for this planet? And how do you know there's only one?
Yeah, that's a great question. So when it comes to discovering the planet itself, finding where it is, we're much better off doing that from the ground. Why? Space missions, like say the Hubble Space Telescope, is kind of like a sniper rifle, where yes, you can see far away, and it's got great resolving power, but its field of view is tiny. So you're not going to use that tool to find something, to search a large area of the sky. That said, the moment we do find it, right, from the ground, we will do extensive follow-up observations to learn about what its surface looks like, what its spectrum looks like, all of these things from space.
Is that how usually objects are researched in astronomy, that you first need to make a ground observation and then you send a space mission to follow up and to get a more detailed view?
For this type of science, yes. There are exceptions. Extrasolar planets, for example. The most successful mission has been the Kepler mission, which just took a patch of the sky, which was slightly above the galactic plane, and just stared at it for like 3 years, right? So it found 5,000 planets or something like that with that method. So it really varies on the problem that you're working on.
Thank you. All right. Sorry, we have a question right in the back there.
Yeah, I heard you talk about the planets being ejected from the entire atmosphere or the entire solar system. How do they get ejected? Is that the black hole? And is Earth in line for any of that?
Okay. Well, so no, the Earth is perfectly safe. We will destroy ourselves far sooner than we get ejected from the solar. So generically speaking, as it turns out, you can think of it this way. If you wait long enough, every planetary system is unstable, right? Just from the gravitational pulls, mutual gravitational pulls that the planets exert upon one another, every planetary system will eventually fall apart. But it takes, oh my God, it takes so long. It takes so long that we can't even calculate how long it takes. How do the objects get ejected from the solar system? They get ejected by scattering. So when objects come close to Neptune or Jupiter, they get gravitational kicks. Right. I mean, it's just like what we would when we launch spacecraft. We call this a gravity assist, where you use the gravity of some planet to accelerate an object. Well, in case of Neptune and Jupiter, that gravity assist gives you so much speed that you're actually going faster than the escape velocity from the sun. So indeed, when the solar system forms and undergoes its chaotic and kind of dramatic rearrangement, you lose a ton of material. And this is true for every planetary system that forms. Every planetary system forms through a chaotic episode, but the Earth is safe.
Remember, this guy thinks in terms of 4 billion years. You know, we only have time to take 2 very short questions, and I see Ben.
No, guess first.
Okay.
So my understanding is that what clued us into dark matter and dark energy was unexplained galactic motion. So what is it about solar system unexplained motion at that level that confines you to be looking for visible objects and not dark, unseeable matter or energy?
Yeah, that's a great question. Basically, dark matter in case of galaxies was a solution of last resort. It is the least uncomfortable solution that you can have. So dark matter is really diffuse, so it would actually be very difficult to get the requisite amount of a dark matter halo around the sun to do what we need to do. The reason we are looking for the planet is because Occam's razor tells us that the simplest solution is almost always the right one. So we need to first rule out the possibility that there's this planetary object before we go to any other more exotic explanation.
Okay, and I think we're going to take Ben's question next, and maybe you can stick around to answer all the other questions later.
I believe I heard you say that Neptune was discovered within an hour. Was it Neptune?
Yeah, Neptune.
Of when the search began. Mm-hmm. And last night I heard you say that it could be this October. And on the stage I heard you say it might be 10 years. Yeah. My question is, which is it?
So if you come back tomorrow, it might. Remember, all of these timescales are small compared to 1 billion
4 billion years, yeah.
Where would you put the probabilities of those 3?
Yeah, so this is a notoriously difficult thing to predict, right? In case of Neptune, actually the telescopes had been good enough to discover Neptune for many decades by the time it was discovered. People just didn't know exactly where to look, and the sky indeed has many, many stars. We could find Planet 9 as early as this year, right? In October is kind of when the right part of the sky comes up, right? So when we search for it, we might get lucky and find it in October. But to give you a scale, over the last 2 years, we have been observing every fall as much as we can, and we covered about 25% of the search area, right? So that's kind of we are indeed operating, unfortunately, on a decadal time scale, and there's, say, a 10% chance we might find it this year. Okay?
All right, so here's to hoping that it really happens. Thank you so much.